All right, so good evening, everyone, and welcome back to another lecture for cloud computing, winter 2023 semester at Oakland University. In the last class, we had basically wrapped up our discussion on the first module, learning module that we have for this course, which was basically computer clusters, right? So just to quickly give you a recap of what we had covered in that particular chapter is basically we have an idea of the evolution of the paradigm shift. Okay, so in terms of the different computer architectures and the different computer systems and networks that was initially present and how they evolved over time due to the functional requirements of our society, right? We learned about the fact that things started off as HPC, high performance computing, and then on the other end of the spectrum, there was HTC, and that kind of evolved. And currently being around the 2010 time, as far as the evolution chart covers, we had things like Internet Web 2.0, and it has evolved further in the next 10 years from then. We had also the concepts of cloud computing due to virtualization, which was the foundation or the cornerstone of cloud computing. And then basically embedding sensing technologies, we got the infrastructure for Internet of Things, right? So we also learned about computer clusters, okay, where basically the whole idea was to kind of pull together the resources that was just sitting idle in the form of commodity hardware, software, and then kind of execute different parallel jobs on these computer clusters so that we can efficiently use the resources that was available to us, and also kind of improve the speed of execution of different computer intensive tasks, right, or computationally intensive tasks. Another important thing that was something that computer clusters provided us with is the fact that we can scale the resources as needed, because these computer clusters were essentially built. The philosophy was to build these computer clusters using everyday machines, right? So that was easily available to us instead of using previously, as we were using before, computer clusters were basically supercomputers as the nodes of these networks, right? So that philosophy changed, and computer cluster brought into the picture many kind of benefits. But in addition to that, there were also certain design challenges that was present in the form of, let's say, scalability was there, availability was there, and one of the important design challenges which kind of enables the implementation of computer clusters is that we can actually pool the resources together as like this single resource, which can then be facilitated to the user, and the user will be unaware of the distribution of resources of the underlying platform was through the help of this software that was known as a single system image, or as an acronym, we call it SSI. And SSI in itself had its own research challenges, implementation challenges, and stuff like that, right? So this eventually became the backbone of the infrastructure for the current generation cloud computing that we know now. Because essentially there were different classifications of computer clusters that was available to us. So it was in the form of compute clusters, load balancing clusters, and then highly available computer clusters as well. So those were the main three types of computer clusters, right? So this became from a hardware perspective, this paradigm became the backbone of cloud, right? So from here, you can achieve what is known as a computational grid, right? If you are building a computer cluster that was specifically responsible for executing high intensive computing applications, or if your goal was to support data, large amount of data, then you were looking at a data grid, right, instead of a computational grid. So essentially, this is what forms the backbone of cloud computing, right? But implementation wise, from a functional standpoint, just having the infrastructure was not sufficient, right? So this is the junction that we stand at right now. And to get to cloud computing, we essentially have to learn three more things, right? So we have to learn one of the important technologies which actually enables or makes computer clusters much more better, right? In terms of resource sharing, in terms of scalability, and in terms of distributing the services that they can support to their clients on an ad hoc basis, right? Or an on-demand fashion, right? So that enabling technology is basically what we know as virtualization. Okay. So once we understand this technology then needs to be applied to the underlying infrastructure that enables cloud computing, right? So when virtualization is applied to computer clusters, essentially what we get are basically virtual clusters. Okay, so this will basically be the third chapter. So this is the second chapter that we are going to start discussing today. And when you develop virtual clusters, you essentially need a way to host them, right? In order to set it up, you need a physical location where you can host the computer clusters, on top of which you apply virtualization and create virtual clusters as well as virtual servers, right? And that hosting mechanism is what we come to know as are basically called data centers. Okay. So once we get to this point, then we can start our discussion on the architecture of cloud computing. That is, how does it combine all of the advantages of the technologies that we have discussed before and all of the different architectures that we have discussed, and how does that bring together to create something that we are familiar with in this day and age, right? So this is the third chapter, fourth chapter, and then once we reach the fifth chapter, essentially we start discussing about cloud computing, and then from this point onwards we move on towards learning about the different aspects of a particular cloud service provider, which will be Amazon Web Services in our case, right? So this is where we stand, and this is how we are going to proceed, right? So to get an understanding of first we now have the understanding of the infrastructure, then we get an understanding of the technology, and then how to apply that technology to the infrastructure to create something completely different, and then how to host that new infrastructure in different physical areas, how the setup is done, and then enable the actual architecture, which is the focal point of this course's learning paradigm, which is basically cloud computing. Okay? So with that in mind, let's start our discussion on formally what is virtualization, right? So of course, we have an intuitive understanding of what it does, right? We basically know that if a physical computer, which has some sort of CPU power, okay, it has some sort of CPU power, it has some sort of memory, and it has some sort of storage, right? Memory being the RAM and CPU being the processing power that is there. So this is some of the fundamental resources that are available to every physical machine that we are aware of, right? And in addition to this, if you want to say, you can also talk about the input-output devices, okay, or the peripheral devices that are associated with it. So in terms of hardware resources, these are some of the major different hardware resources that is available to us. And this is present in every physical machine that we can think of. Well, with the exception of the input-output devices, because some devices, as we learned in computer clusters, if they are very tightly packaged, then they need not be connected to peripheral devices, all right? So the goal here is informally speaking, we want to maximize the utility of these available resources. And then to maximize them, what we do is we basically share these resources, right? So the term for that is multiplexing. And then we dispense these resources to different users and support the applications that they are trying to execute if they don't have the availability of sufficient hardware resources on that they own and they manage in order to execute their application, right? So that is like the informal intuition behind the concept of virtualization, right? So formally speaking, what we are looking at is that the fact that virtualization is a technology, okay, it's a computer architecture technology, which utilizes or which makes the use of different or various virtual machines that are shared. So multiplexing is also shared with an added layer of definition around it that you can switch between the shared resources. So for example, if you are using a car, right, and your friend is also using a car, you're not using the car at the same time, right, in terms of who is driving it, right? So if you switch between the drivers and you're sharing the same car, and let's say your friend goes to work during a night shift or an evening shift, and you go to work during the morning shift, so basically you are switching between yourselves the resource, the single resource that is available to you. So that in a way is what the formal meaning or the sense behind the word multiplexing is. So a computer architecture technology, which basically is enabled by the creation of virtual machines that are multiplexed on the same hardware resource. Right? So that is basically the formal definition of virtualization. So the keywords that you have to kind of remember here if you're explaining virtualization to somebody in as precise of a fashion as you can are basically the fact that it is a technology, right? It is not an architecture in itself, right? It is an enabled technology for computer architecture, and it uses virtual machines, or it enables the creation of virtual machines. And these virtual machines are basically multiplexed on the same hardware resource, the underlying asset or the underlying hardware on top of which you are basically implementing or executing virtualization, right? So, and then why is it useful? The motivation behind virtualization, why virtualization came into being, we all understand this, it's kind of straightforward, is that it enhances resource sharing, right? And it enhances resource utilization. So some of the multiple example scenarios that we talked about during computer clusters, when we had a brief discussion about virtualization technology, we learned the fact that let's say if you have like a 3.2 gigahertz CPU, and then you have 32 gigabytes of RAM, and then you have like 1 terabyte of storage on a single hardware platform. And if you personally are not using all of these resources to its fullest capacity, right, you're not utilizing it perfectly, right? So what you do is you can kind of partition some of these resources, create virtual machines that will use a part of these resources. So maybe you can create like 3 virtual machines of 4 gigabytes of RAM and share the CPU cycles here, and then share a little bit of the storage, let's say like 100 gigabytes or 256 gigabytes and stuff like that. So that way, through resource sharing, you are increasing or making more efficient resource utilization, right? So the last point or the last motivation behind virtualization is the concept of application flexibility. Now, is there anybody who would like to talk a little bit about what this means and how this is a motivation behind the implementation of virtualization technology? Is the question clear?
Well, like an application, like if you're on a Mac and you have to run applications that don't run on a Mac, you virtualize on a different operating system to be able to run those.
Right. So that will be one point, that if you have an application that requires a certain platform which you do not have, or which the underlying hardware does not support, then you can create a virtual machine and create the environment within that virtual machine that will essentially assist the execution of the application that you're trying to run. Yes, Faris.
Professor, how are we supposed to support an application or a software on a virtual machine if the hardware components does not support it?
No, the hardware components are not dependent on the software. So there is a layer of separation, right? So if you're executing an application, right, the hardware, let's say if you have a MacBook or what is the desktop version called, like an iMac, right? I think that's the name. So that compared to, let's say, if you have a Windows PC or a Windows laptop, the underlying hardware is not different. Do you see what I'm trying to say here?
Yes, but while you were explaining, you were trying to elaborate, you were trying to explain that even the hardware components are not supportive. That's why we use virtual machines.
No. The hardware components is supported. The platform that is required to execute the app, you're talking about application flexibility here, right?
Yes.
Right. So the application flexibility is not hardware dependent. It's basically platform dependent. So if your original machine, your local computer that has all of these different hardware resources, If it does not support the host OS does not support the platform that is necessary to execute a particular application, then you can choose to create a virtual machine, okay, and then allocate some of the underlying hardware resources such that it can be treated as a real machine by whoever is using it, and then recreate or generate an environment that will support the application that needs to be executed, which is not supported by the host OS. Does that make sense?
Yes, thank you.
Yeah, okay. So that's one point of it. That is very true. But let's look at another spectrum. Let's take another case scenario and think about it this way. What if it was not a question about the platform being incompatible? So you use a virtual machine to create the platform that will allow you to execute your application. Let's say your host OS does have the platform that is necessary to execute the application. Then why would you create virtual machines? Is this part of the question clear? So the initial discussion that we just had right now, and some of you just contributed to it, is the fact that let's say you have an hardware resource here, okay, and on top of it, for now, let's just assume that there is a host operating system. Okay, and the host operating system doesn't have the environment that is necessary to run a particular application. Okay, it does not have the required libraries and all those things, right? So you create the virtual machine. You have the host OS basically allocate some of the available resources of the underlying hardware, and then you create an image of the guest operating system. Okay, so here we will just call it as guest because this operating system, and this can be whatever operating system that you need in order to run your application within this environment, right? So we talked about this, but what if there is no distinction between this guest OS and this host OS, and let's just assume that the host OS is capable of supporting the requirements of your application. In such a scenario, if you create virtual machines, right, where the guest OS is the same as the underlying distribution of the OS that you have, and let's say the environment is also present to execute your application, is there still any benefit for virtualization? And how does that relate to application flexibility? Yes.
I think in that case, in case I need some additional libraries, maybe those are heavy, and I just want it occasionally. Let's say for my performance testing, I need it occasionally for a few days only. And I can create a virtual environment, do all my testing, and then I can just switch it off and can start it again whenever I need it.
Right.
It won't be taking my processing power, additional processing power when not in use.
Right. Yes. Others?
Yeah, if you don't need a high intensive, you just need service.
Okay.
Yeah, you just need many small services.
Correct. Okay. Others?
I believe it would be a safe environment,
Very good.
sandbox-like environment, in
Good.
case we are trying to do any testing that will not affect my main operating system.
Good. Lisa? Yeah.
Yeah, so also it's just like if you have different users and you want them to access the same device and you don't want them to allocate the whole resources, so you're allocating a set amount of resources toward separate users. And I think also you can limit their kind of like an access control to each user.
Yes, correct. Anybody else? No? Good. So to just summarize all that you said, and it was in the correct direction. So the first aspect from a security access control that you all have contributed to or discussed is basically isolation, right? So of course, if you are multiplexing the utilization of the same underlying asset, right, you would want some kind of separation, either in terms of security concern, either in terms of privacy concern. You don't want things to kind of crosstalk with each other, that is multiple users application should not be crosstalking to each other, or you should not be able to execute your code environment in somebody else's environment and stuff like that. So that allows you to create. So once you create VMs, we will learn that later on within VMs, you can create containers. So using this technology, you can basically achieve isolation, and that is something that gives you better flexibility in terms of security and privacy concerns that you may have. The other part is if you need something that is temporary in nature. So for the case of testing that one of you were mentioned, right? That is also something that can be enabled by VMs, okay? If you create a sandbox environment, then you can load whatever aspect you need within that sandbox environment, execute it, and then there are multiple options of what to do with that sandbox environment once you're done with it, right? So some of the options is that you can put it to sleep, right? You can put it to sleep, or you can put it to standby, and then you can resume it whenever you want, right? The other options is that you can migrate it to a different hardware resource, right? You can move it to somewhere, let's say, that is closer to your access point in order to reduce the latency of your communication with the VM environment, right? So there is a concept in virtualization we will learn when we go towards virtual clusters, which is the concept of live migration, right? So you're basically moving the virtual machine that is running on a particular physical resource and then moving it somewhere else for whatever reason or whatever motivation that you have, which mostly is related or tied up to the performance of your execution of your environment, right? So these are some of the options. You can also essentially save the image of your entire virtual machine environment, and you can put it in a data storage, right? So you can store it in a database, or you can store it, let's say, if you're thinking specifically with respect to AWS, they have these buckets, right? So S3 buckets are there, which is their simple storage service. So you can create an image of your entire VM environment, not just the booting environment, but whatever operations you have, whatever applications that you have installed and stuff like that, and you can save it. So the next time that you ever want to use that environment, you can just boot it up and everything will be ready to go at that point of time. You don't have to install things. You don't have to set it up from scratch, right? So these are some of the essentially the motivations behind the category of application flexibility that can be enabled by virtualization, right? Through the implementation of multiple VMs that are multiplexed on the same hardware machine, right? So again, just a quick reminder is the fact that you need to remember the keywords that essentially build up the formal definition, right? So the fact that virtualization is a technology, the fact that it is enabled by the implementation of multiple VMs that are multiplexed on the same hardware machine, right? So this is how essentially you will want to remember the definition, right? So moving forward,
Professor, what does that mean by multiplex here?
Switching. So when you share the resources at the same time, you won't use the same portion of the resources. We talked about the car example, right? So the car is one underlying hardware, right? And let's say two people are sharing that, but two people cannot be the drivers at the same time. So you need to switch between who gets to use the resources at one point of time. Make sense?
Okay.
You good?
Yeah, okay.
Okay. All right. So moving forward, so we need to first, not first, but once we understand what the formalized definition of virtualization is and what is the motivation behind virtualization, the next step in our learning journey is to basically understand where can you implement virtualization, right? And to understand that, we need to basically look at the architecture of a traditional computer, right, or a standalone computer, and we need to look at the different layers that is essentially available where you can implement the virtualization technology, right? So if you look at a very traditional computer, we all are familiar with the fact that it has an underlying hardware, okay, which has some kind of processing power, some kind of memory in the form of RAM. It has some kind of storage and stuff like that, okay, and some kind of IO devices that are associated with it. On top of the hardware, you have the host operating system that is running, right? So remember that there will be two different terms that we will be using as we move forward when it comes to operating system. Is that for the actual physical machine, if there is an operating system that has been installed on top of it, we will call it the host operating system, okay, or the host OS. And then for any virtual machine that we create and load it with an operating system, and that operating system can be of the same distribution as the host, or it could be a different distribution. But in terms of naming, in terms of terminology, we will call that operating system that runs within the VM environment as the guest operating system. So that is basically the two types of operating system that in terms of terminologies, we will be referring to in these discussions going forward, okay? So in a traditional machine, we only have a host operating system. There is no VM running on top of a traditional machine. And then on top of the operating systems, you have your different applications. Now the applications need the underlying resources from time to time. So whenever they do need a resources, they will submit their request to the operating system, and the operating system will essentially talk to the hardware and then deploy or allocate the resources that the application has requested, okay? Or how to schedule the jobs of the execution of the applications and things like that, right? So on top of this, when you create virtualization, you need the help of another software that allows you to actually implement the virtualization technology. You cannot just simply, out of the blue, using magic, just start creating virtual machines, right? You cannot do that. So what happens, and then the architecture is a little bit different depending on how you want to implement this technology. But the most important or the crucial piece of the puzzle that enables virtualization is basically this software, okay, that is known as a hypervisor, or sometimes it is also called a virtual machine manager, right? So without this software, you cannot essentially create the virtual machines, right? So there are two different architectures of how this software will be implemented or plugged in to your traditional machines so that it can support virtual machines. And we will talk about that in probably the next few slides. But what is important from this particular image here is for you to remember that the software that is actually responsible for implementing the virtualization technology is called the hypervisor, or sometimes it is also called the virtual machine manager. In the cloud environment, we basically use this term more often, which is the hypervisor. So this is what your takeaway is from this image. And when you create virtual machines, you create it on top of the virtualization layer, right? So this is the layer that will be present and that will separate the underlying from the VMs that you're going to create. Now, how this is implemented is going to be we will have two options and we'll talk about it. But when you create the VMs, okay, the VMs will have their own share of the underlying hardware, and that will be enabled by the hypervisor. So any kind of request that a VM needs to make, remember that in the traditional computer, we talked about the fact that anytime an application needs to use the underlying resources, it talks to the host operating system, right? However, when we come to the scenario of virtualization's implementation, then any kind of resources that the VM wants, they need to submit that request to the virtualization layer, okay? Sometimes this is also known as the middleware, okay, that enables virtualization as well, right? So it's essentially a software and it's known as the hypervisor. So then the hypervisor figures out what the request is, and depending on the architecture for the implementation of hypervisors, it will either communicate directly with the underlying hardware, or it will communicate with the host OS on top of which it is running. So basically, those are the two available architectures that are available. Inside the virtual machines, you will have a guest operating system, okay, an image of an operating system. And again, remember, the guest operating system's distribution can be the same as the host operating system if it exists, the distribution of the host operating system, or it can be different, okay? And also remember another like quirky fact is that it is not necessary for every architecture to have a host operating system. Okay, and we will see when that particular case is, right? And on top of that, you have your applications, right? So these applications can be then self-isolated further inside what we call as containers, okay? So that way, these applications which are running can be further separated in terms of their boundaries from each other, and they do not invade each other's memory space that they're using or any kind of file hierarchy that they're trying to access and stuff like that, right? So looking at the architecture of hypervisors or VMMs that we know as, so basically what they are, again, the keywords, they are basically a software, okay? And it creates an abstraction of virtual machines, all right? And the way they do that is they implement different virtualization layers, okay, on various levels of a computer system. So what we need to know now is a few things here that stands out. We, of course, all understand what the software is. What do you understand by creating an abstraction of VM? So to rephrase this question, what do you understand by abstraction as a concept? And can you elaborate that with an example that maybe does not belong to this domain and it's a little bit more simple to understand for everybody?
I always view it as a layer that abstracts the upper layer from the lower layers from that layer.
Yeah, from a technical standpoint, that is true. But can somebody explain this as if we are not familiar with the concept of object-oriented programming? Can you give like a very simple example that can help some people understand that?
It would let an application think that it's running in the OS that it was designed for, and it would just run not knowing what the hardware is, and it's totally doesn't know. So it's abstracted.
Correct. Again, can we simplify it further? Can we take an example from everyday life where we can see abstraction? See, this is what you have to think, right? Most of us understand the technological definitions, but when you're having everyday conversations, right, you would want to aim for explanations that people can relate to. And of course, we can all relate to coding and application execution, guest environment, but can we do better? Can we simplify our example further?
Concept that isn't clear to everyone, that has maybe multiple layers of understanding.
With an example, can you elaborate? Think about it.
Professor, it may means I'm not really sure. I'm just guessing. Like it can be a basic feature of an OS. It will provide the base thing. Like if I need a database, it will give me basic database related things only. It will not put in a lot of other things which may be required by some other application. So it is kind of creating an abstraction layer.
You're all correct, but what I'm looking for is a much more simplistic example.
Let me try this.
Yeah.
What if you are a diner in a restaurant? You have
Okay.
no idea what foods are and how to make them.
Yes.
You just you order a meal and you get it, and you're totally abstracted how the meal was created and what the ingredients are, but you enjoy the meal.
Correct. You're right. Let's try another example. If everybody understood what he just said, that is right. That is what I'm looking for. Tell me, how is abstraction implemented in this scenario? You're a driver of a car. How do you see abstraction here?
You basically don't see all the mechanisms that are happening inside. You just use the driver, the wheel, stick shift, or whatever you can see. You don't see what's in the hood, basically.
Correct, right? So the dining example, that is correct. This car example, that is correct, right? So essentially, if you want to boil down abstraction to its most simplest form, what you say is need to know basis information that is required for a user or anybody else who's using the service to execute the service, right? So to take the car example, you don't know the internal mechanisms of the car, what is happening here, right? But as a driver, you have a dashboard that has been given to you that gives you some understanding of the internal operations of the car. You have a gas pedal. If you press that, it accelerates. You don't know how the acceleration mechanism actually happens, but you have been given an endpoint for which you have the understanding of what you need to do with it, right? Similarly, you have brakes, and when you press the brake, the car will decelerate or the car will come to a full stop, right? But you don't know the internal mechanism of how it is being implemented, right? So all the technological examples that every one of you gave was actually correct, but to relate it to something that is everyday makes your explanation better, right? It's not that technical examples are not appreciated, but if you're trying to convey some piece of information to somebody, it always helps to first think of the most simplest way that you can explain. So once you explain this scenario, then you can probably, talk about APIs and stuff like that, and then creating methods or interfaces that will be enabling or implementing the concept of abstraction in actual programming, right? And things like that. And you can keep on moving further and further. So here also, when you do an abstraction of the VMs, like as the initial discussions went, right? The people, the users who are going to be using the VMs, they will think of that as a standalone physical machine. They will not have an understanding of how it has been created, where it has been implemented, but they have been given all of the resources or the endpoints that is necessary for them to be able to execute their tasks, right? So that could be in the form of hosting, let's say, a web server. It could be in the form of executing a program or creating an IDK environment, and things like that, an IDE environment, and all those sort of things, right? So that is why we say that the hypervisor, which is a software, creates an abstraction of VMs by implementing virtualization layers at various levels of a computer system, right? So that brings us to the second part of the definition, which is the implementation of virtualization on various levels of a computer system, right? So if we look at this diagram, there are certain things that will be intuitively evident, right? That in terms of what are the different layers of a computer system, right? So you can think of the first layer is the hardware layer, then you have the operating system layer, and then you have the application layer. But on top of this is the one that is just evident and popping out to us. But there are two more layers along with this, and the one that is even below in terms of complexity of a hardware level is known as the instruction set architecture level, okay, or sometimes also used by the acronym ISA, right? So remember that every computer that is built has a type of instruction set architecture, and this is something that you should have discussed when you have taken an algorithmic design and analysis class, because without knowing what an instruction set is, you cannot necessarily evaluate the complexity of an algorithm in terms of how much time it takes to execute it, right? So you might have heard that nowadays the Windows distribution machines that is being built is running on the x86 architecture, right? Sometimes when you download different softwares, it gives you the option that whether you're downloading it for a 64-bit architecture or whether you're downloading it for a 32-bit architecture, right? Slowly and slowly, we are now all moving towards the 64-bit. 32-bit is kind of becoming less and less utilized and stuff like that. But this is essentially the level of instruction set architecture where you specify on a bit level, right, how different operations will be carried out or executed and how much time it takes to basically execute these different options, right? So we can look into arithmetic operations. We can think of gates that are flipping the arithmetic operations, and then essentially they are performing subtraction operations. You have different ways of performing multiplications and those kind of operations, right? So depending on the instruction set architecture that you use, the execution time of different processes on your computer is going to take different times, right? And essentially, when we learn algorithms, we create this hypothetical RAM, which has its own instruction set that allows us to generalize the different algorithms that we create and then to analyze them so that we can get some uniformity and some universal applications to the algorithms that we are trying to analyze, essentially, right? So you can implement virtualization on the instruction set architecture level, but as the whole concept suggests, that it is going to be a very painful task. That is the complexity of implementation of virtualization on the instruction set architecture is a very tedious task, because we will see that you essentially have to create an interpreter that can take the code, like the bit level code of one architecture, and then translate that to whichever platform that you're trying to kind of migrate that code to, right? So that is a very hectic task, and we'll revisit this again when we discuss what are the examples of some of the technologies that enable these layers of abstraction. Okay, then we talked about hardware level, OS level, and application level. We understand these levels. This is intuitive in nature, so I'm not going to just keep on discussing this. The last one, which is not as evident as the instruction set architecture, is the library support level. So this begs the question now is, what is a library? And what do you understand by performing virtualization on the library level, or the library support level, not the library level? So let's start with the first question. What is a library? What do you understand in its most simplest form? Let's say you're coding, right? You're programming, you're doing some development, and somebody tells you that you need this and that library. What does that mean?
Basically, would have variables and methods that you can refer to and use. Instead of rewriting the code, you can just use the library in different codes.
Correct. So to do something, to achieve something, you don't have to write the code from the scratch. Basically, somebody has already done that for you. And through abstraction, again, coming there, you essentially import or link those libraries with your program, and then execute the functionalities that, or the support that those libraries provide you with, right? So it could be in the form of different methods. It generally is in the form of different method calls, right? So you do a function call, but you don't know the body of the function. But as long as you understand the prototyping, you can execute that. So depending on the language that you're using, these libraries or have different names, right? So sometimes you might see it being called as packages, right? Sometimes you will be calling them as header files. Okay, in the realm of C, C++, C# and stuff like that. Packages are there for Python and stuff like that. And especially if you're doing things like web programming or web development, right? It is in the form of something that we call as APIs, right? We don't call in web development or mobile development, we don't essentially call them as packages or header file. There's a separate set of libraries for that. But essentially, the virtualization part that is applicable is through the application of APIs, or application programming interfaces, that you can essentially embed or link up with your actual application. So for example, if you take, let's say you're doing a data science project or a data analysis project that requires you to check how COVID affected people, right? And the way you want to do this is to basically harvest all, let's say, the Twitters or the tweets that has been made with a particular hashtag that relates to COVID. So your first step is to gather your data. So, and when you want to gather the data, you essentially need to bring all of the tweets into, let's say, a file or a database, whatever, or however you want to store it. So in order to do that, you have two options. One is you write from scratch the logic that will allow you to harvest the data from Twitter, or you can use some of the existing APIs that can be essentially just linked to your program, and you just need to make a call to those APIs, and then the API will do their job, right? So what happens is, in such a situation, right, API is not just a single version, okay? And how people are using the API and what data that API is generating is not going to be the same for every user, right? So if you apply virtualization there, then essentially the layer where you're applying virtualization is at the library support level, when you're virtualizing these different APIs for different people or different users to use it based on their requirement, right? And not the same way that it is intended to. So going forward, just to dive a little bit deeper, so application level, some of the famous examples that you might have heard before is the JVM, or the Java Virtual Machine, right? So that kind of enables the portability of Java code, right? So when we were learning about C, C++ and we were migrating into Java, this was one of the essential discussions that we had, is that Java is extremely portable back then, and back then was, well, quite a while ago. But essentially JVM is an example of application level virtualization, right? It can also kind of do virtualization for all the processes that are executing, right? You can create isolated app environments because of this, okay? And then this sometimes is also known as sandboxing. So for example, in terms of sandboxing, if you want to think about it this way, if you have ever worked with Django, which is a web development framework for Python, right? Then one of the initial steps of Django is to create a virtual environment, such that all of the different application libraries that you need will be essentially isolated and captured within that single virtual execution environment, right? So it is not spread across on your actual physical system, right? So that is one of the examples of application level. On the library support level, there are these different technologies that enables the library support. Okay, and what essentially the takeaway is, and what you have to remember is all of these different APIs that are available. Then you can virtualize those APIs, and then you can dispense the services to different users, and these users will use these APIs according to their requirement and generate the data based on the functionality that they're trying to execute. Okay, on the operating system level, when you create the virtual environments, okay, what you are creating are basically known as isolated containers. All right, there is actually a certain distinction between isolated containers and virtual machines. All right, we will talk about that in probably like 2 or 3 more slides. But what you need to remember is when you apply the concept of virtualization on the operating system layer, what you end up getting are known as containers. Okay, so these are basically environment or resources that are co-located in this single container or this single box, and they are isolated from different users, okay, that are using that same operating system. All right, so that is basically what the operating system levels virtualization is. And then we have the hardware itself, where you're creating, like you have different enabling technologies such as the VMware. You might have heard about that. The Zen architecture is one of the initial hypervisors that was available in order to create hardware level abstraction or hardware level virtualization. And what this is doing is that this level of virtualization is directly communicating, bypassing the operating system itself with the underlying resources, and then they are virtualizing them and then providing it to the users. Okay, so the only difference that hardware level abstraction versus operating system level abstraction is that the operating system abstraction, whenever the VMs that are running on top of it, whenever that needs hardware resources, it needs to communicate through the operating system layer. Okay, and if the virtualization layer is embedded or built on top of the hardware, bypassing the host operating system that is there, then whatever request the virtual machine makes, that needs to be handled by the hypervisor itself. And the hypervisor directly communicates with the underlying resources, that is in the terms of processes, memory, IO devices, storage, and stuff like that. And finally, you have the instruction set architecture. What it enables is basically it creates an interpreter. All right, in the most simplest way of explaining this, when you're trying to implement ISA level virtualization, what you are basically implementing is an interpreter that is responsible for transforming the code of that runs on a particular platform to something that can be executed on any kind of instruction architecture set, right? So something that you have to remember. So a use case example of when instruction set architecture level virtualization will be important is, for example, if an organization has a lot of legacy binary code or code that runs on very old languages like Pascal or COBOL and stuff like that, and you want to migrate that to the cloud computing environment, which are running more newer or current generation platforms, right? So that way, it doesn't have the instruction set to support those codes, which was written probably 30, 40, at this time it is what? Almost 70s, right? So almost like 50 to 40 years now, right? So it doesn't support those instruction sets. So if you want to migrate that to the cloud computing platform, essentially you need to implement virtualization on the instruction set architecture. Okay, so is the levels of virtualization abstraction clear? Does everybody understand on a conceptual level what these 5 different levels are? What virtualization does when you apply it there? Does everybody have a basic understanding?
Yes.
Yes? Okay. You can also use emojis. I think that's like the craze right now if you're too shy of speaking. So at least I know that people are there. Okay, we have a few popping up. It's like stars in the night sky because everything is blank. All right. So that begs a question from all of you, is that how do you decide when to choose to implement which type of abstraction there? Or where do you want to implement virtualization? So to rephrase the question again, how would I make a decision? Let's say if you are responsible towards developing your cloud computing infrastructure, right? So that means you will bring a computer cluster together. And then the next step basically for your journey is to implement virtualization. So you have downloaded a hypervisor, but now you need to know on which layer do you want to implement the virtualization. So can you start a discussion for a case-by-case basis of what or how will you decide which layer of virtualization to implement? When will it be beneficial and when will it be a detrimental aspect towards the implementation of your platform? Is the question clear? First and foremost.
Yeah.
Yeah. So go ahead. Where would you start? What goes through your head? What's the first thing that you would ask yourself?
I would start at the top level and determine if there needs to be the same level, like the same type of applications or libraries or operating system level, and just go down. If I need different variations, then that's when you would need to virtualize.
Yes. So that is the intuitive way of going about it, is that you know that there are 5 levels. You either start with the bottom up approach or you start with the top down approach, right? Start with each layer. Ask yourself from an organizational perspective, is that use case something that you will be supporting, right? And if the answer to that is yes, then it will pass your preliminary check, right? Then you keep going down, let's say, as Sean explained, right? A top-down approach. So you start from the application, move towards library, OS, hardware, and instruction, right? And then ask yourself, do I need this? Do I need this? Am I supporting any sort of functionality like this? Am I going to dispense any kind of services like this? And then you figure out what you want to do, right? But this will only allow you to identify whether you need something or not, right? Whether that will actually be suitable for you or do you need to find an alternative to it is something that you also have to figure out, right? And that plays into the final, service models of cloud computing as well, as how cloud computing came into being with 3 popular service model that we know in the current day and age, which is infrastructure as a service, platform as a service, and software as a service, because there's a direct correlation on how those service models were implemented and how that correlates to this set of virtualization layers that we have in front of us, right? So this requires us to trace a few steps back and think a little bit more generically and not in terms of all these architectures and stuff like that, right? Is the fact that whenever you're trying to decide on something, and we talked about this, we had a discussion about optimization, right? And again, we know the fact that optimization requires certain factors that can be tangibly evaluated, right? Less subjective in nature, and to give it a more quantitative perspective, right? So there are 2 perspectives, right? One is the qualitative perspective when you're evaluating something or assessing something, and then there's the numerical or the quantitative perspective, right? So in order to study this, you need to be able to understand the performance of each different levels of virtualization with respect to different performance metrics, right? So if you are trying to evaluate, let's say, a routing protocol for your networking purposes, right? If you're trying to evaluate the effectiveness of a security protocol that you have designed and stuff like that from a research point of view, the validation always needs to be done through a performance analysis. And anytime you want to perform a performance analysis, you need certain performance metrics that are generic in nature and is applicable to the scenario where you're trying to perform that performance analysis, right? So here, when it comes to evaluating the effectiveness of different levels of virtualization implementation, right, there are 4 different performance metrics that are available to us. So the first one is to basically assess which level of virtualization will give you the best performance. Because remember, depending on where you are implementing it and how difficult it is to implement, the performance may vary. All right. Then the second metric is the flexibility of the applications. Remember, one of the motivations that we discussed when we were talking about virtualization is the application flexibility. So that is also one of the metrics to evaluate the efficiency or the effectiveness of the different implementation levels. Then there is the complexity of implementation. Okay, if something is very good but very hard to achieve, then that is something that is not reasonable. Right? So, for example, we are running out of resources on Earth, and then you might say that, oh, there are a lot of resources on some other planet in the solar system, right? I also heard that there's also a planet where it rains diamond or something like that. I don't know if that's true, but you can check and let me know. I think there is a moon or a planet where actually it rains diamond because the surface pressure is so high. Okay, let me know if that is true. You can act as the role of a myth buster, right? And then finally, but to go and harvest that diamond, it's so costly, right? It actually defeats the purpose. To finish my thought, and then finally, what is the level of security and privacy, right? So that can be kind of wrapped around the metric of application isolation, right? So how this table has been set up is that for wherever you have the highest number of X's, okay, or these marks, that is the top in the category. Right. So to take an example here in terms of performance, that what yields the best performance if you apply virtualization to that layer, then you have either the hardware level virtualization or the OS level virtualization. Okay. The mid category is basically the runtime library support. And then after that, the third one is the user application level. And then the least performance is basically achieved through instruction set architecture. Okay. Can somebody tell me why?
Can you repeat the question?
So can you reason as to why implementing virtualization on the instruction set architecture level has the least performance compared to the other layers of virtualization implementation?
Because you're transforming the code set to a lot of different possibilities, like you're transforming an old code set to a new code set.
Yes.
It can be really it can be really intensive and
It
requires
is
a lot of
very
physical.
intensive.
Yeah.
Absolutely. Right. First, you want to add something?
Not really, but what I thought is that the hardware would be compatible the most with the hardware set installed initially on the device. So changing that would cause more computation in order to adapt.
So are you saying that the hardware is changed?
Not really, but the instruction set fed to the hardware would change. So in order to make it compatible, it would require more computing, right?
So you're talking about ISA and why its performance is bad, right?
Yes.
Yes. Yes. Right. So to bring those 2 points together, right, you need to create, once you transform this, a compatibility of whatever you are essentially transforming to multiple different platforms. And that is really an intensive process. And remember, at the end of the day, the way the virtualization is implemented for ISA is through code interpretation, okay, or emulating the code and allowing it to run on different platforms, right? So that is done by executing an interpreter. There is no compiler support for that, right? So it would take line by line all the lines of code for a very long program, right? And it has to go through all of them and then translate that or interpret that to wherever you're trying to migrate this application. So that is why the performance takes a lot of time, right? But if you are able to achieve that, now you are sitting with a process, right, that can be executed on any platform or any architecture, right? So as a result of that, you can see that the application flexibility for ISA is like inversely proportional to each other, right? When it's compared to the performance, right? So ISA virtualization, essentially, as a result of that translation of architecture, gives you the highest application flexibility. And then the second one is basically hardware level virtualization. And tied up at third place, you get the same level of application flexibility, whether you implement OS level, runtime library support, or user level virtualizations. Okay. In terms of implementation complexity, though, the hardware level virtualization and user application level virtualization are the most costliest to implement. Okay, and then followed by in the second level, you have OS level virtualization and instruction set virtualization. Okay, implementation complexity versus performance is not the same thing. So don't get confused by it, right? Just because they have good performance doesn't necessarily mean that they will be easy to implement as well. All right. So, and the last one is basically in terms of implementing the cost of implementing, the lowest level is runtime library support. So again, question is, why do you think hardware level virtualization and user application level virtualization are the costliest to implement? Now think in terms of cost, the complexity of the implementation, not in terms of performance. Separate yourself from that idea for a second and ask yourself, what would it take for us to be able to implement a layer of virtualization on a hardware? Think about it from that perspective. What will you answer?
You have to take into account all the hardware.
And as a
Any
result
hardware.
of that, you have to change
Yeah.
what is already there, right?
Yeah.
And that will not allow you, but that will result in additional cost, because now you have to modify the hardware, bring in new components of that hardware, and that hardware becomes something entirely different in order to support the virtualization than what it originally was. And that takes money. Okay. What about user application level? Why is that also costly to implement?
You have to make sure all the features and functions work.
Correct.
One little thing would make it
Break
unusable. Yeah.
Yeah.
So
right. So the isolation environment that you're creating for all the different virtual versions of your application, you need to make sure that they behave in the same way. Any small twist and turn in the implementation of that virtualization layer will either break the application, make it malfunction, and that is going to impact your reputation, right? Or you being the service provider. Okay. And then finally, in terms of application isolation, that is what provides the highest level of separation when it comes to privacy and security concern. The best in the feature is user application level. Okay. And then right after that, following in second category, you have hardware level virtualization. Third is instruction set architecture. And then the last level is basically OS level and runtime level. All right. So taking all these performance metrics into mind, all right, now if you average it out, what do you think is the best option for you to select? So if you forget for a second your use case scenario, which technically you shouldn't, but let's say for the sake of having this argument, if I forget my use case scenario, and if I pose you a general question that given the performance analysis based on these metrics, what do you think your top contender is for the implementation of the virtualization layer? Or where should you implement it? Then what your answer would be? Can you take a quick look, analyze the results real quick, and tell me what your thoughts are? Which one do you think is the best? Well, not the best, but comparatively better than the rest.
On hardware level virtualization.
Okay, so let me just say 1 point for hardware level. Anybody else?
OS level.
Okay. OS level. What else? Think about it for a second. It also helps for you to be able to kind of take a look and understand where you, like in terms of your analysis, you should be able to have a keen eye, right? So you know here that the legend says that whichever is 5x is top in the category, but you need to be a little bit clever, because just being top in the category doesn't make it best in the category. So for example, in this metric, if you're top in the category, it's actually the inverse, right? It doesn't mean that you're the best.
Yeah.
Yeah, right.
Right. So when you're analyzing it, you should have that keen eye. When you're thinking, right, you should be able to know what are the differences between the different metrics, what they relay. And when you're averaging that information out, that should be in the back of your head, right? So here, an easy way, but not easy way, but the straightforward intuitive way to look at is that, oh, I see hardware is 5x here, 3x, 4x here, and then 5x here. So this should be the best. But for this, the inverse is true, right? So that means if it is 5x in the implementation complexity category, it actually makes it a bad choice, right? If you're just thinking in that category. So when you average it out, you have to keep that information in mind when you're trying to implement it, right? So essentially, you have to find something in between. So here, the lowest implementation, this becomes the best category, right? But if you average it out across the other categories, it's not the best, right? It's kind of somewhere in between. So the second option that you look at is you check the next 5x category. So you have the OS level here. It is kind of midway here, okay? So basically second. So it's not that bad. It's in between the worst and the best, right? And then you have somewhere in between here for these two, okay? Nothing too extreme. So it essentially OS level kind of lies in between, right? The scales of top and worst, right? Top and bottom, it kind of lies around there. So as we discussed in decision-making processes, it's always about trade-off, right? You cannot have the best of everything. So when you want to do a trade-off, when you're trying to optimize something, essentially what you're trying to achieve is a balanced output, right? Not too bad, not too good. Well, because not too good is because you couldn't achieve it, not because of choice. You don't want to select something which is not too good, right? So that's why we kind of rest at OS level virtualization. And this is a foreshadowing, essentially, because our next set of discussion will essentially discuss what does cloud computing prefer, or how cloud computing was built, right? So that brings us to one of a side information, right? So when you think of cloud computing, there are service models, okay? And these service models are essentially what is provided as a service that we know of to the users, right? And there are three major service models. There are alternative, like other models that are cropping up as well, but the primary are the fundamental ones with which cloud computing was built. So you had the infrastructure as a service, you had the platform as a service, and then you had the software as a service. So now if I pose another question and tell you that, let's say you are building your own cloud computing infrastructure, right? And these are the service models that you plan to create. So if you had to pick one level of implementation of virtualization that can be mapped to each of these service models, what will your answer be? So that means if you want to implement software as a service, does everybody understand software as a service? That's the first question. Otherwise, you cannot answer this question. Is there a general consensus of what software as a service means?
Yeah.
General. Okay. I have to assume that 3 out of 23 or something is general. Well, not even 23. It's without me, that's 29 participants. Okay. So which level of implementation would you choose for software as a service? Quickly.
User application level.
There we go. So I will take this and I will map this to this guy. What about platform as a service?
OS level.
Okay, so we will take OS level and map it to, and then infrastructure as a service.
Hardware level.
Thank you. So now the next question would be, what about runtime library support? Where would that go?
Lies in between platform as a service and software as a service.
Correct. So this, remember, this is basically embedded for platform as a service. So this can be implemented within the containers that will be deployed for the VMs that will support platform as a service for the environment support. Okay. And what about ISA?
Maybe in between the infrastructure and platform as service.
Okay, so ISA is very specific in nature, so
Yeah.
you cannot generalize it. Okay, so you wouldn't find ISA level virtualizations in any of the existing service models. It can be embedded within infrastructure as a service, but what it is primarily used for is basically legacy app migration. Okay, so if a business has a particular case, user case scenario where they have a very big chunk of a code base for legacy applications using very, very old languages, and that needs to be moved onto cloud computing, then you need a dedicated space for that to be executed, right? And then in those situations is when you are going to implement ISA level, right? It's very time consuming in nature as well. So you wouldn't get that in the everyday service models that we are familiar with. Okay, so keep that in mind. All right. So what are the design requirements then? We understand what virtualization is. We understand the different abstraction levels of virtualizations of where for a computer system's different layer can it be implemented, how the performance varies in such implementations, what are the good choices, what are the decent choices, so to speak, and what are the case-by-case choices, and how they map to the service models that we know, the traditional well-known service models of cloud computing. Okay. Right now, there are more than these three, right? But these are not as, those are not as popular as these ones, right? Everybody should know this three, okay? So what are the design requirements? So that means that when you are building the hypervisor that will essentially be responsible for implementing these layers of virtualization on a system level of your choice, right? Or a level of your choice, what should be one of the important design criteria that it should keep in mind? And there is only one requirement, okay? And that is the most important requirement. So, and this connects back to the concept of transparency again. So if you are basically partitioning the resources of the underlying asset, then your users should not experience a slowdown in terms of the performance within those environments. Okay, so to formally talk about this, that any kind of program or process that you run within the virtual environment, it should behave, okay, the same way as if it is running on a standalone physical computing machine, right, or a physical computer. That is the only requirement that needs to be ensured by the hypervisor or the virtual machine manager or VMM that will be implemented on top of the either the guest operating system or the hardware resources itself, right? And then the other requirement is that the VMM should have a control over the system resources, either by communicating through the operating system or directly in contact with the hardware itself, right? The only time there is an exception to this rule, this design requirement that is there, is if you are in a situation where the availability of system resources takes a higher preference over the execution of other applications that are running on top of the same underlying, then there can be a violation of this particular rule, okay? Also, if there is a timing dependency on one of the applications, right, that is causing some kind of delay in all of the other applications that is being supported by the underlying, then that can also be used as an exception to violate the design requirement rules for the VMMs or the hypervisor, right? So the takeaways from this slide, the two things that you have to remember is that the major design requirement for any hypervisor that you develop and you try to use is the fact that any kind of process program that will run within the virtual machine environment will behave exactly the same way, or at least close to it, right, without too much degradation, as if it was running on its own physical system, right? So users needs to be transparent from the fact that there is a virtual resource that has been allocated to them, right? To them, they need to think that they are as if working on their own physical machine, okay, or own personal computer. And this hypervisor would have full control over the system resources because it is the responsibility of the hypervisor to implement virtualization. And as a result of that, if the hypervisor cannot control the system resources that are available, then it will not be effectively able to implement the virtualization technology. And the other takeaway from this design requirement is that there can be an exception in two scenarios to the rule that your application needs to run the same as if it's running on the original machine, is where there is a higher preference of availability for a particular VM. So the other VMs needs to be kind of demoted in that scenario in terms of the availability of resources. Or there is a VM that, due to any kind of timing dependencies or data dependency, is basically choking the resources and making the other VMs behave in a less favorable fashion, right? So in those situations, the hypervisor can make a executive decision to essentially, stop some of the VMs or put them in standby until the situation has been resolved. Okay, so that brings us, so now we understand levels of abstraction, we understand the design requirements. So the next step is to basically understand the architecture of hypervisors. That is how hypervisors can essentially be implemented. Okay, and there are just two different types of architecture, and they are pretty straightforward to understand here, right? Essentially, what it boils down to when understanding the type of architectures that can implement or using which you can implement hypervisors is basically to ask this question that who controls or how do you control the underlying system resources? That is how the hypervisor controls the underlying system resources. If you understand the answer to this question, then essentially you know the difference between the two types of architectures for hypervisors that is available to us. So essentially, the two types are called either type 1 or type 2 hypervisors. Type 1 is also known as bare metal hypervisor. Okay, bare metal hypervisor. And then type 2 is known as a hosted hypervisor. All right, and how the architecture is designed is that we know that at the very bottom layer, we have our system resources, hardware resources. If you implement the hypervisor directly on top of this hardware resources, okay, then basically that is a type 1 hypervisor or a bare metal hypervisor. On top of this hypervisor, you have all your different VM virtual machines. And within that, you can have a guest operating system. Okay, you can have a share of the resources, and then you have all the different types of applications that are running, etc., etc. And the same goes here. Okay, whenever a VM needs to request any kind of underlying resources, then that request will be submitted to the hypervisor, depending on, again, there are different variations of this architecture. We will talk about that. But generally speaking, the hypervisor here has complete control over the hardware, right? So it will take that request and then communicate directly with the hardware and then allocate the resources back to the VM that has requested it. All right. Type 2 hypervisor, or as the name suggests, hosted hypervisor, it is hosted by something, as the name should intuitively suggest to you. So in this architectural scenario, at the very bottom layer, again, you have the same thing. You have the hardware, but on top of the hardware, you have a host operating system that is running. Okay. And then on top of the host operating system is where you implement the hypervisor. So this architecture essentially is that of a type 2 or hosted hypervisor. And what happens after this is more or less the same. Okay, so you have your VMs, you have your guest OS, and then you have your apps running within these environments, and you can create containers within them, right? So anytime a resource request needs to be made, it goes to the hypervisor submits it to the operating system. The kernel in the operating system, which is the lowest level of the operating system, then communicates with the actual hardware and then sends the response back through the OS to the hypervisor and then eventually to the virtual machine that is running. Okay, so does everybody understand this two distinction of what is a type 1 hypervisor versus a type 2 hypervisor?
How does the hypervisor communicate with the hardware in bare metal? Does it have its own kernel?
Yeah. Okay. So if you understand this, I'm assuming that everybody understands the basic difference. So it boils down to the control point. right? Does the hypervisor need to go through the operating system, the host operating system, or can it directly communicate with the hardware? So just to trace back, the question that was asked is that how does the hypervisor communicate with the hardware directly? It has its own kernel layer here. Okay, so there is basically a piece of kernel that is within the hypervisor that allows it to communicate with the hardware. Okay, so that is how it enables the hypervisor. So if everybody understands the distinction between these two architectures, and of course, there are some examples, you can read about these examples that are listed in the slides. Okay, so one of the well-known hosted hypervisors are VMware Player. I have it on my machine. If you have ever used it, let's say to run a Linux environment on your Windows PCs without creating two different operating systems, essentially running on top of Windows, right? Then you use the VMware Player. So that is an example of a hosted hypervisor. Then one of the most earliest hypervisors that was a bare metal hypervisor is the Xen server architecture. Okay, and now the more famous ones or the more popular ones are the Oracle VM server and the Microsoft's Hyper-V, right? So these are the ones that are used by enterprises. A quick note here is cloud computing uses bare metal. We don't have an exact number, but if you want to put it into perspective, more than 80% of cloud computing infrastructure's implementation actually uses bare metal hypervisors and not hosted hypervisors, right? So with that, we segue into our next discussion is when would you choose which type of architecture? Like, again, it's a decision-making process, right? And you will find plenty of this happening in this course till we finish the conceptual part, is that since you have two options, which one will you choose, right? And the moment you get this question, you need to ask yourself, okay, how do I evaluate my choices, right? Are there certain things that can be essentially assessed in order to come to a decision in a more rational way, right? Rather than just intuition. So the few things or the metrics that we generally use for to kind of facilitate the discussion on which type of hypervisor architecture is good, whether it is bare metal or hosted, okay? Then the first question is which has a higher or a lower latency, however you want to take this question, and then which one is more secure. So go ahead.
I'd say type 1 would be more secure because you're interfacing directly from the hypervisor to the hardware, as opposed to going through a host OS, which could introduce more security vulnerabilities in that communication.
Okay, what about type 1? Sorry, what about latency? Okay, let's trace back again. Can I get a contradicting argument to type 2 being more secure than type 1? Just to kind of exercise your thought process. Can somebody contradict type 1 being less secure than type 2? Technically, you can't, but can you at least give it a try? First of, yeah, go ahead.
we might say that type 1 is closer to the hardware, so it's less secure.
Okay, that's one way of putting it.
But that security can be implemented in hypervisor as well. Like whatever is there in OS, it can be part of hypervisor directly from security point of view.
Okay.
I think type 1 is equally secure, like should not be a problem. Depends on the implementation.
Well, I would ask is when you say secure, what security are you looking at and at what level? Okay, if you're saying, hey, is my communication directly to the hardware, is that the one that I'm trying to secure? Well, obviously, the closer you're to the hardware, the better, because you don't have another software that you're going through. But in the other side of it is, what if there's something wrong with the hardware? You're using a safety island in that hardware, and somehow something goes wrong, then you have no other abstraction. So again, it depends on what you're trying to do. That's how I see it. And
Okay.
what are your motivations pretty much, or the things that the risk that you can take.
So that will take us back to some of the questions. So one of the questions that I will ask you is that, think about it for a second. Of all your years being involved in this field, right? I mean, when I say the field, I mean computing in general, right? Being familiar with computers. If I tell somebody that I work with Windows operating system versus a Linux distribution, right? Or Mac OS. And then I tell somebody that I'm using a Zen hypervisor, a Zen server hypervisor. What do you think that people will be more familiar with?
The
operating system,
The
and not the
operating system,
hypervisor.
right? So this holds true for the community. Do we agree to that? Like the general community, right? So when you think of, now let's bring in another, like hold on to this piece of information, and let's revisit this discussion where we were talking about what type of security that we're trying to achieve, right? So before we even decide that, can you tell me what are the different types of attack that can actually take place when we are talking with respect to this portion of the architecture, right? Around here and then around here. Like what type of attacks are you thinking of? Like, can you first tell me of attacks that can actually, like, how do you attack the hardware? What are the different ways in which, because that is basically where you are trying to do the exploit, right? Either through the communications, whatever happens, or through the system calls of the kernel that the hardware recognizes. But essentially, the goal is to kind of mess up the allocation process, right? So how can you attack the hardware? What are the different ways?
You can hijack a service on the host OS that communicates with the hardware, overload it.
Sure. So one of the attack vectors or attack surface is basically this host OS, right? Any other ways? So when I say attack the hardware, it doesn't have to be something that is fruitful. You see what I'm saying? Because you have to remember that if you think of the pillars of security, right? And I'm not putting in authentication authorization, just think of that being embedded into CNI. If you think of availability, that is also one of the avenues of protection that you need to ensure, right? And not every time there has to be a end game for the attacks that you're causing. Sometimes it's just about disruption. So if you think of it that way, other than hijacking the host OS, where you can do malfunction and stuff like that, if you just want to disrupt, then you are doing physical attacks. You are tampering with the system itself, right? So that it just doesn't work. The service is not available, right? So now, what are the entry points? So the hardware can be affected here as well, right? Physically speaking. So the protection here, how do we protect that? Come on, how do you protect the hardware? Think simply. Don't go too complex.
Physical security.
Physical
locking.
protection.
Yes, physical protection. Put it somewhere
Yeah.
in the building that is well monitored, locked up, secured. One entry point in the building, one exit point in the building, right? No multiple access points. Cool, right? What about now? So we will just ignore the physical attack part of it, right? Because we know that it can happen in both architectures. Okay, not a problem. I mean, it is a problem, but you apply good levels of security, physical security, in order to make sure there is no unauthorized access to the physical devices itself. Now, here we talked about the fact that the host OS can be hijacked, right? And can something similar happen to a hypervisor as well?
Yeah.
Yes, but now bring the previous thought that I told you all to kind of hold on to. That is, which one is the general community more familiar with and what they try to go after?
Host OS.
The OS. Yeah.
Yeah, so there are like malware attacks that are specifically designed to exploit the operating system, right? And the level of security and the understanding of the importance of the hypervisors architecture is low comparatively to an operating system's distribution. I'm not saying that it is non-existent, I'm not saying that nobody will choose to attack the hypervisor and mess up the allocation of resources. It is possible, but from a likelihood point of view, remember we talked about risk assessment, where the tangible thing that we will evaluate is how likely is something that can happen, right? So if you put it on scales, comparing this host operating system versus hypervisor, then the host operating system has more weight in terms of how tempting does it look and how many attacks are known to infect a host operating system compared to the hypervisors, right? So from a secure perspective, generally speaking, if you're not evaluating it on a case-by-case basis, then type 1 hypervisors are more secure, right? But of course, there will be other discussions as well, that if you are sure about the operating system that lies between the hypervisor and the hardware level itself, right, then you get another level of abstraction there. So if your operating system is somehow more hardened than regular operating systems, then maybe you can survive with the type 2 architecture as well, right? So this is all evaluation discussions, right? There is no absolute answer as such that, hey, this is what it is. But if you just look at the bare minimum evaluations and comparison between the security of type 1 and type 1 is always better, right? And essentially cloud providers use that in majority compared to type 2. All right. The other thing is, when you kind of merge this discussion to latency, which one is going to give you a lower latency?
Probably type 1.
Not probably. Type 1 is going to give you a lower latency.
Obviously, yeah.
Yeah, because the rationale is kind of pretty in front of us, is that you don't have to go through another hop of system calls, right? The operating system doesn't need to manage another software that is directly asking for resources and then respond back to it, and then it responds back to the VMs, right? So instead of that, if the hypervisor is in direct command of the hardwares, right, then it can essentially allocate the resources or respond to the requests much more faster compared to a type 2 hypervisor. So together, when you merge these two discussion points together, like this point here and this point here, then how would you answer this question? When would you choose which type? It doesn't mean that the type 2 hypervisors are useless, right? There is still some purpose to it, as we learned about it through the example here. Where did the example go? This VMware workstation. So think about it in this direction. How many of you are familiar, or have you ever used VMware Workstation Player, where you can launch it, load an image of, let's say, Ubuntu, something like that, or Fedora, in order to do a data analysis task, and then it runs on top of your system, right? So try to think of this. When will you use this?
Type 2 you'd probably use for like user-facing scenarios.
Yeah.
Wanted to deploy to a set number of users in a company to different application, you'd use a type 2 or hosted virtual machine. Whereas type 1, that's if you're a cloud computing provider or you want to maximize your security and performance and minimize your latency, you do bare metal.
Perfect. Okay. So I hope everybody understands that if you're just running front-facing applications, let's say, previously we were having this discussion that, oh, you're doing a unit testing, right? Or you're trying to create a sandbox environment that requires a distribution that is different from that of your host operating system, right? Or you are a small scale to a medium scale organization, and then you want to provide a platform that all your employees can use in order to do the development tasks and stuff like that, without them having to go through the implementation of different libraries, APIs, and stuff like that, right? In a situation like that, all you do is you install these type 2 hypervisors on the individual computers or on the computer clusters, and then everybody can access it, right? But if you're looking at a very large scale organization, so for example, like HP is one of the examples because they had their own private cloud and stuff like that. Or if you're looking at the modern day cloud service providers whose main business is to provide service, basically different resources as a service, right? Then you typically kind of revert to the usage of type 1 hypervisors because they are essentially more secure. And then in terms of performance, they also give you better results as well, right? So those are the two different kind of use case discussion when it comes to which one do you want to choose. Yes, sir.
Is it more difficult to implement type 1 than type
Yes.
2?
Yes. There will be some modifications of the hardware that will be involved for us to be able to directly implement hypervisors on top of the hardware itself. And we will talk about it in a few slides. Okay. Does that answer your question?
Yes, thank you.
Yeah. Okay. So let's take a side step here and let's pose this question. This is an interesting question. And this is an important question as well. Typically, if you're going to be working in this domain, is what is the difference between a container versus a hypervisor? Because some of you may be familiar with these things, right, which are kind of roaming around like Dockers, or then you have an orchestration service, which is Kubernetes. It's just not, I forgot the spelling, so that's why I stopped Kubernetes. I think this is the one. Okay, so this is a Kuber, okay, and then NETES, if I'm not wrong. But this is an orchestration and a container service, and not just a container service. This is a purely container service. Okay, so these are basically containers. Some of you might be familiar with, and then we just talked about hypervisor in a little bit details, right? So one of the important things, and this is pretty important, okay, if need be memorized for the time being until you get used to the muscle memory, that what are the difference between them, right? And the major technical difference between a hypervisor, which is software, and container is basically an environment, is that the containers allows different applications to run independent of the operating system. That is the whole ideology of a container. It is basically decoupled from the software, right? And whatever platform that you are on, as long as there is something that we call as the container engine. So for example, in Docker's case, there will be a Docker engine. Then you will be able to execute your applications within that container environment, right? As a result of these features, containers are extremely portable. But remember, the only dependency that containers have are basically the containers engine that can execute the containers environment, depending on. So if you're using Docker, you need to have the Docker engine to execute that, right? In contrast to that, hypervisors are basically responsible for running operating systems independent of the underlying hardware by the creation of virtual machines. So know and remember that the primary purpose of hypervisors is to develop virtual machines. Okay, and when it develops these virtual machines, it does not, or it decouples the creation of these virtual machines from the underlying hardware. So if you think about it this way, that containers decouples the application's execution, any application's execution, from the underlying software and hardware platforms, whereas an hypervisor, through the creation of virtual machines, basically executes any type of operating system independent of the underlying hardware. Okay, so by doing so, hypervisors enable the sharing of computing, storage, and memory. And the way it can be implemented is either through type 1 architecture that is directly communicating with the hardware, or it can be implemented as a hosted hypervisor that it is communicating with the host operating system, and then through that, the hardware. So please remember these two definitions, because the trapdoor situation, why we are talking about this, is sometimes people confuse VMs as containers. That causes isolation. Okay, but this is not true. Yes.
Can we say that hypervisors abstracts away the hardware, meanwhile containers abstracts the operating system?
No, containers don't abstract the operating system. Containers just create an environment that allows an application to run independent of the operating system. So there is no abstraction of the operating system itself. You can have multiple containers within a particular virtual machine. So containers don't care about what operating systems there are. Does that make sense? And you can run any type of different operating system within a virtual machine, irrespective of the type of hardware where you're trying to host it.
Oh, got it. Yeah.
Okay. Make
Okay,
sure this
thank you.
distinction is clear, because this is a trapdoor question. If you ever fall into an interview situation, is people will try to trick you by asking or trying to confuse you about the fact of the conceptual difference between the containers and virtual machines. Okay, so if necessary, to begin with, memorize this until you factually understand what the differences are. Remember, given the nature of containers, you can have multiple containers inside of a virtual machine. Okay, there is no problem. And each container will be responsible for the execution of a certain type of apps. Containers do not care what operating system is underlying. And of course, hardware, right? As long as something is available in terms of resources. Whereas hypervisors run different operating systems, irrespective of what hardware lies underneath it, through the creation of virtual machines. That is the major distinction factor, right? So please revise this concept and make sure that you fundamentally understand the difference. All right. So now the last concept, and we will wrap up here, but just to tell you what we will discuss from here onwards, is we understand what virtualization is, just to recap the class. We understand the different levels of virtualization's implementation. We understood the performance analysis of these different layers of virtualization implementation. We understood the software, which is the hypervisor that is essentially responsible for implementing the concept of virtualization technology. And we talked about the two different type of architectures that are available to implement the hypervisor, right? So from here onwards, what remains is to discuss what type of virtualization does cloud computing actually use, right? It is not a straightforward version of OS level virtualization, even though we kind of, looking at a higher glance from the performance analysis, accepted or understood the fact that OS level lies somewhere in between, right? It's not too bad, and it's not that great compared to everything else. But if you average out all of the different metrics, then it falls in a good optimal balance, right? But the discussion that we are about to have in the next class, not now, is how OS level virtualization is actually better than hardware level virtualization. And as a result of that, why cloud computing does not use OS level virtualization. Okay, so that is like a tricky cliffhanger, but I think you will enjoy the discussion here, is that even though OS was better, why did cloud computing choose something that is not purely OS, but somewhere in between, right, of OS and hardware. All right, so we will wrap up here, and I will stop the recording, and I will see you all again online. Not online, sorry, in person next Monday during class hours. All right, so this is not allowing me. All right. Okay, so bye-bye, and see you all on Monday.
Have a good weekend. Thank you.
All right.